Okay, everyone. Well, this talk is about a collaboration with Microsoft at Station Q in Santa Barbara. And the person who did most of the work here is Herb Ness, who's a postdoc in my group at King's College London. And this project is about trying to develop the next generation conventional computer. So this is not a quantum computer, but a conventional computer. And let's see if I can, yeah. The idea is to use, build on something that's already been around for a long time, which are MRAM devices. MRAM devices work by stacking two magnetic films between a tunnel barrier, as you can see here. And when the two magnetic layers are aligned parallel or when they're aligned anti-parallel, you get different resistances. And exploiting that fact, you can make very high dense random access memory. So it works in practice because you can pin one layer and free another layer. And by applying a pulse field through a wire nearby, you can flip it. So you can get a switch. So JMRAM is similar, but the cladding layers, rather than being they're not just regular non-magnets, they're superconducting instead. So the principle is a little bit different. And the advantage is that the voltages that you require go down by a factor of 100 or so. And that means the clock speeds, at least theoretically, can go up by a factor of 100. So you could really make a computer much, much faster than you can today. But still, it's still a binary computer. It's not a quantum computer. So what is JMRAM? Well, the J stands for Josephson junction. So it's a junction consisting of superconducting. It's a superconductor that's got a non-magnetic layer sandwiched between two N leads. And the M is a modification of the Josephson junction by replacing the normal metal in the middle by a ferromagnet. And then the RAM comes by stacking these Josephson junctions together the same way you do ordinary RAM. So I'm going to spend a few slides talking about how, what the physics is that makes such a thing actually work as a memory device or a switch. So first, just a review of the Josephson effect. In a conventional superconductor, you have some macroscopic wave function, and it's a Cooper pair that consists of two single particle states. There's a typo there. Oh, no, it's not. Yeah, it should say psi up plus k and psi down minus k, coupled by some coupling field, which is some boson. And in the conventional case, it's just electron-photon interaction. This is what the famous theory of Bardeen, Cooper, and Schrieffer developed. Because of that, that pairing field, delta, states that would be degenerate, the plus and minus k states that would be degenerate at the Fermi level, open up and form a gap. And you can see it from that little 2x2 Hamiltonian. That's what you expect would happen. Now, if you start from a superconductor and now clad a normal metal C with superconductors on both sides, that normal metal doesn't have a gap. So the superconducting wave function has to tunnel between A and B. So the Cooper pair on, say, on the left would have to tunnel into the one on the right, or vice versa. And it's this effect that is the basis of a squid, for example. It works because there's a phase shift. There's the macroscopic wave function has a phase shift on the left and on the right, and the C region changes the phase on the left relative to the right. That phase shift is the all-important thing. So how do you, how does it work? Well, imagine that you have a superconductor on the left, a superconductor on the right. then you have an electron that propagates from the left to the right. And at the same time, a hole has to propagate from the right to the left. And because it's tunneling, the macroscopic wave functions decays as you propagate through the normal region. And the rate of decay is some length, which written here is psi, which is the Fermi velocity times the thickness. Times the time. And the theory, Usadel, I think, was the first to write it down. It shows you that the theory says that the current should go proportional to the sine of the phase. And the phase meaning the phase shift of the left relative to the right. So in a non-magnetic metal, you have in this simple picture, you have a parabolic band structure, and the energy at Kf and the energy at minus Kf, those two different states are equal. However, if you have a ferromagnetic metal instead, then this majority spin and the minority spin split by some exchange correlation field. And that splitting means that the K spin up for a fixed energy and the K spin down for the same energy have to be different. So the exchange correlation field causes the wave numbers of K up and K down, which form the Cooper pair, to be different. And as a consequence, the electron and hole quasiparticles accumulate a phase change as you propagate through the region, some length L. The phase change is just the difference K up minus K down times the length L you propagate. And you can estimate the scattering time, and it's proportional to 1 over the splitting field. Now the wave function decays just like in the normal Josephson junction, but the decay rate is faster. And in addition, and this is the important thing, it acquires an oscillatory component. And that's the oscillatory component is what's exploited in the JMRAM device. So in the simple picture, there's some macroscopic wave function or pair correlation function that describes the Cooper pair. And as the last slide showed, it accumulates a phase depending on the length L. And that phase is proportional to the change in the wave number. So in what's called a zero junction, this is the usual Josephson junction case, L is small enough that the phase accumulated is less than pi. And then the current, the supercurrent, is proportional to sine phi. But you can imagine if L is long enough, then you switch to what's called a pi junction, and that's when the phase becomes bigger than pi, or you just redefine the phase as being between 0 and pi, and you write the supercurrent as I times sine of phi minus pi. The key point is that it changes sign. So the supercurrent depends on, the sign of the supercurrent depends on the thickness of the junction. So this is the simple picture, but real materials don't follow the simple picture in the details. The qualitative story is kind of similar, but for one thing, the VXC is not a small number. This model assumes a Taylor series expansion, so VXC is supposed to be small compared to the bandwidth. And that's just not true in the case of a transition metal. And also the bands are not parabolic, and there are lots of bands. So some of the wave numbers, if this simple model were to be applied, you'd have imaginary delta KF or complex delta KF. So the whole theory is just, you don't know how, I mean, there's no way to know how reliable it is. Nevertheless, some junctions have been made, and they do show this oscillatory behavior. And as the simple theory says, if the exchange correlation field is big, so the magnetic moment is large, then the period should be shorter. And that's the case of the cobalt on the left. But if the period is, if the exchange correlation field is small, like it is in nickel, then the period should become longer. And qualitatively, that seems to be the case, that the smaller the exchange splitting, the longer the period. Okay, so how do you exploit that effect to make a switch? Well, imagine that you have two Josephson junction with a sandwich of Josephson junctions shown in the figure. And one of the magnetic regions, the yellow one, is free, whereas the tan one is fixed. So that means that one of them, in the bottom case, the magnetic field always points one way, whereas in the top case, it can be switched just like in the ordinary MRAM. Well, when the case where the two magnetic fields are parallel, then it has to propagate through both top and bottom layers, and the phase shifts that you accumulate add together. However, if the magnetic field of the top layer gets flipped, then the phases of the two regions subtract instead. So you could imagine a case of a stacked layer like this, where the sum of the phases exceeds pi, whereas the difference of the phases is small. So in practice, you have to make a device like this, where you want the phase shifts to be picked sort of on the order of pi over 4, so that if you sum them up, you get something like pi or a little bigger than pi, sufficiently distinct from pi. So this actually is a really cool idea, and in theory it works, and in practice it works. But in practice, the quality of the devices are so low, they're not useful yet. So the next step is to try to model them from a first principles theory to see if we can understand, get a quantitative picture of what's happening rather than just try to extrapolate from these simple models. This slide, this figure here shows you, just imagine that you have a tri-layer, you have a metal on the left, and some scattering region in the middle, and then a metal on the right. And forget about the fact that they're superconducting at the moment. Just the ordinary Landauer-Bodecker theory tells you that an incident wave psi in on the left gets scattered by this middle region, and so psi out is some combination of psi in of waves on the left and waves on the right. So there's some scattering matrix, call it Sn. Now the next step, imagine turning the left and right layers into superconductors. You get an extra scattering from Andreev reflection. And that essentially propagates a whole electron on the left gets scattered into a hole propagating back to the left. So that's something that's missing in an ordinary metal, but it's an extra scattering that occurs in the superconducting case. So when these two scattering events are coherent, you get a bound state. This is what's called an Andreev bound state. And the condition for the bound state to occur is that the wave function psi in has to be equal. You can just combine these equations at the top. And you see that essentially the determinant of SA times Sn has to vanish. So you can get eigenstates right by that condition. And then you can calculate the supercurrent by knowing the eigenstates of the Andreev states as a function of the phase shift phi. So let's now look at SA and Sn in more detail and see what their structure is. The scattering matrix for Andreev reflection basically just scatters electron into a hole and combined with some phase shift. So that's the structure of the matrix that you see. The RA is coupling an electron spin up to a hole spin down. And so it's strictly off diagonal. It's coupling one going plus K to one going minus K. The normal scattering, this is something that's been around for a long time, and you can calculate it within Landauer-Bodecker theory. If we assume no spin flip for now, which means no spin orbit coupling, then a ferromagnet has, for each spin channel, it has some scattering matrix. And it's diagonal in spin, so there is no off-diagonal part. Each one of those scattering matrices, they can be treated as independent. Each one of those scattering matrices consists of a 2x2 matrix. Those 2x2 matrices involve reflection, where a wave incident on the left gets reflected to the left, or a wave incident on the left gets transmitted to the right. And then you also have the two other parts where the wave starts from the right. So this has been a problem that people have been able to solve for a long time. Usually they're Green's function-based methods, and they calculate transmission probabilities such as that formula showed at the top. The problem is that we don't want the big T and the big R, which is what these methods develop. We want the little t and the little r. The little t times its dagger gives you the big T. And the reason why you can't get that in a Green's function method, a normal Green's function method, is because Andreev states involve the relative phases of individual eigenstates of the wave functions, not the Green's function, which does not know about the individual wave functions. The way you solve this is you generate normal modes. So you write the Green's function by decomposing it into normal modes of the bulk left and right. And this can be done by solving a quadratic eigenvalue problem. And the eigenvalues tell you the wave number, and the eigenfunctions are basically, they just tell you the distribution of the states over the orbitals the basis set that you represent it in. So once you've done that, then you can decompose quantities like this vertex that's sitting in the top equation, resolve it by normal modes. And for example, the vertex there is shown how you can decompose it into the velocity matrix. And that makes it possible to determine the little t and the little r. So first thing we did was a benchmark in a non-magnetic case. We picked a barrier, just free electrons on the left and right, and picked a low barrier, just some constant shift. And the theory says that if the transmission becomes very close to close to zero, I think that should say 1, not 0, then the critical current times the normal current should be the gap, the superconducting gap divided by 4. So we use this big, heavy machinery just for this model case to see if we got that. And to establish that we could, in the limit that we had many, many states that the transmission went to 0, that the current resistance product went to delta over 4. Or also in the nearly transparent case where you have just one channel, that the current resistance product also goes to delta over 4. So we did that for some case where the transmission was big but not really quite 1. And you could see that the current voltage, the current resistance product was some number a little bit bigger than 1/4. But it seems to confirm what the simple models describe using this very big hammer. Now we want to look at realistic interfaces, and we looked at a couple. Niobium usually was what's used in practice for the superconducting N leads. And there's some experiments with iron and nickel. And they're very different because iron has a big magnetic field and has a big exchange splitting, whereas nickel is much smaller. So because of the short time, I'm just going to talk a little bit about the iron and forget the nickel. This is what you see if you look as a function of different iron thicknesses. You see Andreev levels. So all those pretty colors on the top 3 panels are different Andreev states as a function of the phase shift phi. So you see there's a whole bunch of them, and you have to sum them all up. And then sum them up, you get this, this blue curve. And you can see that it, at least it has a sort of cosine-like form for the one on the left. And the current is positive for the up to phi less than pi. So that means it's still a 0 junction. If you look at the one on the far right, you see that the current is negative for phi less between 0 and pi, and then it becomes positive beyond pi. So that means that we're clearly in the region of the pi junction. And just at 14 angstroms, or maybe it's a typo, it's more like 10 angstroms. That's a crossover region where, if you notice the scale of the figure, it's down by 1 or 2 orders of magnitude relative to the left and right. So that means that it's very weak, and it's just in the point where it's making a transition between 0 and pi. It's complicated, and you see all those jags because some of those Andreev states, you can see them at the bottom as they go just below the gap, they stop being bound and they introduce non-analytic behavior. Now if we plot the superconducting critical current as a function of thickness, you can see this 0 to pi transition. The current drops to something about 0, and then it's not really that smooth, but you can see it drops below 0 at 18 angstroms. So somewhere in the region of 6 monolayers or so, which is 12 angstroms, there's a 0 pi transition. And that's roughly speaking what the experiment gets. The experiments are a little bit dicey because they have interfacial regions which they don't really know how to pin down very well, but it gets approximately the right description. So just to summarize, to the best of our knowledge, this is the first attempt to simulate a magnetic Josephson junction by making a Bogoliubov transformation of the normal states, and then using the Landau-Bodecker formalism based on density functional theory to give us the scattering matrix of the normal states. And with some modest assumptions, I didn't talk much about the assumptions, there are a couple of assumptions in here. We can solve these equations and obtain the Andreev levels, and then the superconducting current is a function of phi. In the first applications, we found a 0 to pi transition in iron, and we also found one in nickel. The period in nickel was not in great agreement with the experiment, and that's because the nickel exchange splitting in density functional theory is badly described. It's about factor of 2 too large. If we reduce it, then we get much better agreement with the experiment. And the last comment is just that this is all implemented in a publicly available code, which you're free to download. And there's the webpage for it. So that's my story.
Thank you very much, Mark. We don't have any questions at the moment. Has anybody got any questions that they'd like to ask, in person as such? Okay. Seems like it was an all-in presentation where nobody had questions. Very well done.
Okay.
Thank you. Thanks, Mark. Okay, so Cedric, are you okay? Oh, here we go. We do have a question. Apologies.
Oh, okay.
From Tony. Oh, if I can see my chat. So Tony asks, do you worry about interface roughness?
Yes, our currents are much too large compared to the experiment, 1 or 2 orders of magnitude. And the simple theories tell you that the roughness, not only in the surface, but the real materials are not crystals, they're alloys like permalloy. And the simple theories tell you that the behavior is qualitatively different when there's roughness involved. So that's the ultimate goal, is to model real systems, but our first effort was just to see if we could do it at all. It was the first, to my best of my knowledge, it was the first time anybody had modeled this kind of device. So yes,